Mechanics problem from 2006. Looking over my paragraph here, I want to check and make sure that all these numbers are labeled on the picture. 8.2 kilograms, 4.0 kilograms, and 0.7 meters for the height. There's a couple numbers I see that are not labeled on the diagram, and that is the distance of stretching the spring. It says when it's unstretched, it's 0.20 meters, and after we hung the weight on it and stretched it, it moved to 0.25 meters. So that difference is 0.05, and it's that stretching difference that we use in the force formula and the energy formula for a spring. Question A, labeling the forces. Looking at the box on the table has 4 forces. Gravity's pulling down, the normal is pushing up, and those forces have to be in balance with each other always. The string is pulling on this side. We use tension for the string. We can say Ft, or sometimes they just use T for the symbol. And pulling backwards is the spring. Now I know that these two are also in balance with each other because it says the word equilibrium. That means we're not moving. All these forces are in balance with each other. For the hanging block, it has 2 forces. That string is pulling up, tension, it's the same tension, the same string, it's the same tension. Going down, we have the force of gravity on this block, and I labeled these 1 and 2 just to tell them apart in the problems. In general, when we're labeling forces on these diagrams, it's 1 point for each arrow and label. That is correct, and we lose a point for anything that's missing, we lose a point for anything that's extra. Part B, finding the tension in the string, I'm going to look at this diagram here. We know that this tension and this force are going to be balanced with each other because it's again in equilibrium. To show that in a statement, we're using the sum of the forces in the y direction on this block, and we always do the one going in the positive direction subtracting the one in the negative direction. Because they're in equilibrium, they're going to add up to 0. If they were not in balance with each other and it would be accelerating, there'd be unbalanced forces accelerate. This would be equal to m times a. So from this we can get that the tension is equal to the force of gravity, which equals to mg. Then we can just plug in our 4 kilograms times 9.8 and get 39.2. Kilogram meter per second squared is a newton. And we're rounding this to 2 places because 4.0 kilograms is 2 places. Part C, calculate the force constant of the spring. The force constant is the K, so that comes from the spring formula. This was a Hooke's Law lab. The spring constant is K that we're looking for, so we need the force of the spring divided by the X to get our K. Looking at this diagram, we know that that force of the spring is balanced with the tension that we just figured out in Part B. Again, we use the Newton's second law, the sum of the forces in the x direction this time. We do the one going to the right, subtract the one going to the left, and they're going to add up to 0 because they're in equilibrium. Or if they're moving at a constant speed, it would also equal to 0. If the forces are unbalanced, that's when it equals ma. So for this one, our tension is equal to the force of the spring, which equals kx. So we'll divide both sides by x. So we're going to do the tension force divided by x to get our k. Comes out to 784, and again our masses here are measured to 2 significant digits, so I've got to round that to 2 places as 780, and the units for spring constant is newtons per meter, or we can break that down to kilograms per second squared. Either one is acceptable. Part D, calculate the time it takes for the block to fall after we cut the string. So we cut the string and then this block falls straight down. For things that need time, you're doing a kinematics formula. So we need to list out what letters we know. I know right when I'm cutting the string, the initial velocity of this is 0. I know at the distance it's going to fall. I know the acceleration of gravity is pulling it down, and we're looking for the time. So those are the variables that we need. And notice that the gravity and the distance I labeled as negative because they're going in the negative direction downwards. This is the kinematic formula that has those letters in it. And that initial velocity is 0, so we can just cross this part out of the formula. So it's d equals 1/2 at squared. Rearranging for t, 2 slides up, a slides down, and square root. So we have the square root of 2d over a. Plugging those in, notice that I did the negative signs for both the distance and the acceleration because they're both going downwards. Meters are going to cancel. The denominator of a denominator becomes a numerator. So we have, for our unit, seconds squared with a square root is just seconds. We're going to round this one also to 2 places because everything's been measured to 2 places so far. 0.38 seconds. Part E, when I cut that spring, this block is going to oscillate back and forth, and they want to know what is the frequency of those oscillations. What I know for a spring is that there's a period that has to do with the spring constant, and I know that the period is the inverse of the frequency. So I can do two steps. I can find the period using this formula and then do the inverse of that to find the frequency, or I can combine the two formulas together into one. This is what I would like you to try to do, but it doesn't matter which way you do it on the test. All right, so plugging in those numbers comes out to 1.57, and I got to figure out what this unit's going to come out to. Newton is a kilogram meter per second squared. We're dividing it by meters and we're dividing it by kilograms, so I wrote them as separate fractions, and then I can cancel out the meters and kilograms. So this comes out to 1 over seconds, and remember that is the units for hertz. For the last one, we're going to calculate the maximum speed obtained by the block as it oscillates back and forth. To do that, I want to look at a couple sections of the block. This would be the equilibrium position. As the block moves this way, we're squeezing the spring and storing energy in it, and then it stops and starts going backwards, and that block gets faster and faster and faster, changing to kinetic energy. And then it slows down as we're stretching the spring again, and then when it gets to the outside edge, it stops again. So we have only potential energy here stored in the spring, and then that spring pulls it back and it changes back to kinetic. So we're going from kinetic to potential to kinetic to potential to kinetic. So these two energies are going to be equal to each other. So I can substitute their formulas are also going to be equal to each other. We're going to rearrange this for V, so I'm going to multiply by 2, divide by m, and then square root on both sides. This is what it comes out to. And then we'll plug in the numbers here. These units are the same one I had on the previous page. So it comes out to 1 over seconds, but this time we're multiplying it by meters, so we get meters over second for the answer. So 0.49 meters per second. Now a lot of these problems, there's different ways to do them. We can always use kinematic formulas as well. This method is a little bit more difficult, but I want to go through the steps so you can see how it works, because there may be a time when you have to do a problem this way. Looking at the same three positions, I know something about their speeds and their accelerations. Looking at the speeds, I know it stops at this end, it stops at that end, so those are both 0, and in the center it's going to be going the fastest. So it goes slower, 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 stops, faster, faster, fastest, slower, 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 stops, faster, faster, fastest, as it goes back and forth. The accelerations are going to be the opposite of the speeds. And I know the acceleration is doing whatever the force is doing. The force is the strongest when I'm squeezing the spring the most. So this is going to be the strongest force at this end. That's also the strongest acceleration. Same at this end. As I stretch that spring the farthest distance, it's going to have the strongest force on it and the strongest acceleration. In the very center, when you're at the equilibrium position, there's no force and there's no acceleration. So labeling all of those, I'm starting on my way to a kinematics formula. I have an initial speed, a final speed, that's what we're trying to find. I have acceleration, and I know this distance from the information they gave us, that stretch of the spring from the equilibrium position to the farthest stretch was 0.05. So these are all my kinematic letters that I know. All I need to do is figure out the acceleration, and then I can come back and complete this problem. Acceleration comes from Newton's second law, F equals ma. All I need to do is divide by the mass. We found the force on the spring already. I know the mass of the object, so I can divide those and get my acceleration comes out to 4.9 meters per second squared. So this is the kinematic formula that uses all of these letters. However, what we haven't made a big point about in the past is that condition for this formula to work is that we have a constant acceleration. In this problem, you can see the acceleration changes from 0 up to a maximum of 4.9. In a class where we were using calculus, this wouldn't be a problem, but it is a problem for us because we don't have a way of dealing with a changing acceleration. So the trick we're going to use is find the average acceleration over this time. So the average is something you add the two numbers up and divide by 2. So half of 4.9 is 2.45, and I can use that acceleration in the formula. Then when I rearrange this for V final, I'm just square rooting both sides and plugging those numbers in. we end up with the same 0.49 meters per second.